venture this section. We have 3 talks from ICM invited speakers. First speaker is Sourav Chatterjee. He got his PhD in 2005 in statistics at Stanford University. He is currently a professor in Stanford University. He did fundamental work on science method on spin glasses and universality of Rydberg principle. For his achievement, he was awarded a Sloan Fellowship in 2007 and Tweety New Research Award in 2008. He is also actively involved in a series of service to profession. He was an associate editor of Annals of Institute for Health Congress, and currently he is associate editor in Annals of Probability and Probability Theory and related fields. He will talk about a short survey of science method. Let us welcome him with big hands.
Okay, so it's a great pleasure and an honor to be here, and I thank the organizing committee for inviting me, and also the organizers for a wonderfully organized event conference. So I'm going to talk about Stein's method because that's what I started out in my career with, and I'll try to give a very general audience kind of overview of Stein's method, and also my own interpretation of what gives rise to central limit theorem, central limit behavior. So here's the basic assumption. Since it's a general audience talk, I'll assume that the audience has some familiarity with the definitions, rigorous definitions of random variable, expectation variance, central limit theorem, but I'll not assume much more. Okay, so if it was 20 years ago, then or 30 years ago, I would probably have to start with measure theory. But nowadays, people at least know these. So okay, so I can assume these. So the thing is, what do probabilists do? So some of the most common things that we do is we estimate or compute expected values and order of fluctuations of random variables, or we prove generalized central limit theorems, which sometimes distributional limit theorems or on function spaces. In a generalized sense, and a large fraction of papers are one of these. Although you may not explicitly see that, but it's basically this is what we do most of the time. Now, even in these very basic sounding things, there are things that we don't know how to do. So, for instance, for expected values, we don't know how to do in systems like the Ising model or any complicated statistical mechanics models in 3 and higher dimensions. In the order of fluctuations, we don't know, for instance, random combinatorial optimization problems or various other problems. We don't know how to do that. And also, these generalized central limit theorems in the sense of distribution convergence to distributional limits. So, for instance, quantum field theories, or in Martin's talk, what you were hearing about the KPZ thing. So there are lots of these are all part of this, but we don't have any idea how to do anything. So in the context of central limit theorems, let's come to what is Stein's method. Stein's method is a general sort of philosophy which attacks one of these 3 things that I outlined, which is the question of central limit theorems, okay, or distributional limit theorems in general. And it was pioneered by Charles Stein, who is one of the great statisticians of the 20th century. He is still alive, and I had the good fortune of interacting with him when I was at Stanford. So let me tell you what is the basic thing about Stein's method. So first, recall the ordinary central limit theorem. So if x1, x2, etc. are IID random variables, and you take this normalized sum where mu is the mean and sigma squared is the variance, you take this normalized sum, it converges to the Gaussian law. Okay. So the usual method of proof is that this left-hand side is computed using Fourier transforms, and the independence of the summands implies that the Fourier transform decomposes as a product. So that's basically what independence is. and then you can use analysis to complete the proof. So Stein's motivation in the early 70s, actually he started thinking about this in the mid-60s, was that what if the xi's are not exactly independent? Okay. So Fourier transforms are often not very helpful in that situation. So can we build a kind of purely probabilistic machinery to deal with this this kind of issue? So I'll come to examples. So Stein's idea is the following. So let W be any random variable and Z be a standard Gaussian random variable, so which means that this is the probability distribution function of Z. And suppose we wish to show that W is approximately Gaussian in the sense that these quantities are approximately equal for all x. Or more generally, the expectation of some function of W is approximately the expectation of the same function of W for any well-behaved H. So just note that this is a special case of this where you take H to be an indicator function. So if you take H to be 1 if U is less than or equal to x and 0, otherwise this is equal to this. So this is a generalized version of this approximation. Okay. And to put this in context, imagine that W is this thing that I showed in the previous slide, a normalized sum. So if you have this W, imagine it's close to a Gaussian and you want to show this. Okay, so that's the setting. And as I said in the Fourier theoretic approach, you have Fourier transforms, and then you show they're approximately equal. But it may often be hard to write the explicit Fourier transform. So for instance, if you toss a coin n times, a very simple example, if you toss a coin n times, and W with the number of times where you see a certain pattern, HTHH, let's say, or some pattern like this. So you can write down the Fourier transform, and if you're a sufficiently powerful technician, you can analyze it, but it's already becoming kind of difficult, to do this using Fourier transforms. And I'll come to an example where it's basically impossible to do using Fourier transforms later on. So Stein's idea is the following. Given a function h, you obtain a solution to this differential equation. So you take the expectation of h of z, where z is a standard Gaussian random variable. So this is just a constant, this is just numbers. And you take hx minus this constant, and you solve this differential equation. You get a function f. Okay, so that's the first step. You solve this differential equation. Okay. And then what you do is you show that for your given W that you're trying to show to be approximately normal, you have that for this f, expectation of f prime of W minus W if W is close to 0. Using some properties of W, try to show that. Okay. But because of this differential equation, you know that this expectation is exactly equal to this. So you just put expectation, you plug in W in place of x, you take expectation of both sides, and you get this identity. So if you can show this is close to 0, you get this is approximately equal to this. Okay. So that's a very basic step, what you do. So why do you do this relatively complicated looking thing? So what's the gain? The gain is that Stein's method is sort of a local to global approach. So it's often possible to prove that this kind of approximation holds using small local perturbations of W. So when you're doing the Fourier theoretic method, you're doing a global thing. You're looking at W as a whole, and you're decomposing the Fourier transform into a product. So that's dealing with the whole thing. And there is a general notion in mathematics about studying global properties using small local perturbations or study of local things. So often it turns out that in problems you can prove this kind of thing using small perturbations of W. Change W a little bit, and then you're able to somehow show that this kind of an approximation holds. Okay, so that's the main gain, as we will see. And this is the basic equation that you wrote down for normal approximation. Okay, so any questions about this? Okay, so for instance, often one can do the following. You can, given an f, you can cook up some g, so that this side can be written approximately as some constant times expected value of gw prime minus gw, where w prime is a small perturbation of w, which has the same probability distribution as w itself. Okay. So this is okay, for instance, if you toss a coin n times, you check the number of heads. Let's say that's W. So what's a small perturbation that retains a distribution? What you do is you take some number at random between 1 and n. You look at what happened in that toss. Just forget about it. Toss the coin again and put in the new thing there. And then you get a new number of heads, okay? So that's a small perturbation of W, but this new thing also has the same distribution as the old thing, okay? Probabilistically, they have the same distribution. So when you do that, you know that this side is exactly these two are exactly equal because W and W prime have the same distribution. So this side is exactly 0. And so therefore you can conclude that this is approximately 0. So this is known as a method of exchangeable pairs. Okay? So you can try out this whole thing with this simple example, the number of heads if you toss a coin n times, with just this slide and a bit of mathematics, you can prove the central limit theorem by this method, the small perturbation method. Okay, you can, and it basically involves Taylor expansion on this side. So I'll not go into the details of that. So the question is, why does the method work? So somehow, the thing is, if you replace this expectation of h of z by some other number here, other real number, then the solution that you will get will not be well behaved. It will blow up badly at infinity. So this number is the sort of the unique number that makes the solution well behaved at infinity. If you start out with an h that's nice enough. And there's a relationship that's it's because there's a relationship between this differential equation and the Gaussian distribution, and the relationship is made clear by, or you can get a hint of that from this fact that x is standard Gaussian if and only if this is exactly equal to 0 for all f. So that's an if and only if condition. Okay, so for this reason, this differential operator Tf, which is f prime x minus x fx, is called a characterizing operator for the standard Gaussian distribution. And so Stein's method has been generalized to many other settings where you can work with a suitable characterizing operator for a different distribution. Even for convergence of random functions, you can do this. You can, provided you can cook up a suitable characterizing operator, you can employ Stein's method to work things out. Okay, so the history of Stein's method, it's a lot. So my ICM article has the recap of the main developments. Here I'll just say that there are many variants which are called exchangeable pairs, size bias coupling, zero bias couplings, dependency graphs, multivariate and function space versions, Poisson approximation, various other versions, and the key people, some of the people who have developed Stein's method over the years, Charles Stein, Louis Chen, Andrew Bardor, Eric Bolthausen, Larry Goldstein, Kessner Reinhardt, Yoshi Renaud, Vladimir Rotar, so, and others who I have not named. And there are several young people working these days, including myself. So and the good thing is that Stein's method is being used to prove theorems in applied areas. So people have been using it. Various aspects of Stein's method are being continuously used. So it's even after 30 years, or 40 years, it's a thriving area. And there are, as far as the theory is concerned, there are significant opportunities for new results and new applications. So this is sort of a very brief history of Stein's method. So in the rest of the talk, I will talk about a certain interpretation that I have of Stein's method, which I have used for various problems. So, okay. So one of the things that I was thinking about when I just graduated out of my PhD was what is it that makes a random variable approximately Gaussian? Okay, what gives rise to this bell-shaped curve? Okay, so the traditional wisdom is that if W is built out of many small random influences, so it's a sum of many small influences which are approximately independent of each other, then one may expect a Gaussian behavior. Okay, so that's the traditionally how people think about it. So this is clear what it means if W is a sum of independent or approximately independent random variables, but not not otherwise. So I'll give you some examples. So examples where central limit behavior, everybody expects a central limit theorem to be true, but So some examples, but where this heuristic doesn't quite make sense. For instance, one class of problems is from random combinatorial optimization. For instance, minimal spanning trees, random traveling salesman, optimal matching. These kinds of things. You expect central limit behavior. You expect to have central limit theorems, but you can't quite prove it using this kind of heuristic. So let me just give you a little bit of a detail about one example. Let's say the minimal spanning tree. So suppose you have an undirected graph, for instance, a discrete grid. On each edge of the grid there is a random weight. The weights are independent. Okay? So a minimal spanning tree is a subgraph, is a subtree of this graph. So it's a cycle-free subgraph of this tree, of this grid, that minimizes sum of edge weights among all subtrees. Okay. So that's the definition of a minimal spanning tree. And it is expected that under fairly general conditions, the edge weight of total edge weight of a minimal spanning tree should obey a central limit theorem. Okay. So you see, you have this large grid. On each edge you have a weight, and then you are taking all subgraphs of this grid, which are trees, which don't have cycles. Okay? And then you are summing the edge weights of these subgraphs, so which cover all vertices, so subgraphs which cover all vertices, and you are taking the sum of the edge weights, and you're asking the minimum of these things, and so that's supposed to obey a central limit theorem. So so this is actually a solved problem in certain cases. So well, not on lattices. I'm sorry about that. But in okay, so it's okay. It's not proved on integer lattices. It's for the continuum version, but the proofs can be carried over. There are papers by Alexander and by Keskin and Lee which dealt with a slightly different version of this problem, where you have points thrown down at random, and you're looking at the minimal spanning tree of these points. So it is not clear, even in this simpler version where you just have the lattice, it's not clear how this may be seen as a sum of many small influences that are approximately independent. Because to construct this tree, you have to look at the whole graph. Okay, you cannot do it part by part somehow. So it's some function of the whole graph, and you still expect a central limit theorem from this. And so this is a solved problem now, but there are problems in this vein, as I said, the traveling salesman, where it's unsolved. So we still we don't have a proof. There are many other problems where you think it's true, but we don't have a proof. So here I'll outline a heuristic. Well, it's actually a theorem, but we still call it a heuristic. It's an idea as to how can you prove that such complicated random variables, complicated things, have central limit behavior without geometrically breaking up into parts or being able to break up into smaller parts. Okay. So suppose a random variable is a function of independent random variables. So in the case of the minimal spanning tree, we saw it's a function of independent random variables. The edge weights are independent. Okay, so the total edge weight of the minimal spanning tree is a function. It's a complicated function, but it's a function of the random variables. So yeah. Okay. Now let del I of W be the change in W if xi is perturbed. So typically it's replaced by an independent column. So in the simple example that I mentioned, number of heads, if you toss a coin n times, you change one toss, okay, from head to tail or tail to head. The change that you get is del I of W. So how much you change if you perturb one coordinate. Okay. Now this typical size of del I of W, or maybe del I of W squared, it's often called this influence. So it has widespread use in theoretical computer science, machine learning, and many other areas. So people do look at this thing, particularly in the context of proving concentration of concentration inequalities. People look at how a complicated random variable changes if you change one coordinate. So you change one thing, and then how the result changes. So this is a very popular thing of studying objects that arise from random processes. Now the question is, is it true that if the influences are small, okay, so these are independent random variables, and you look at these little influences, and if these are small, W expects central limit behavior. So it's not actually true. So so smallness of these influences guarantees that W has small fluctuations, but it doesn't guarantee central limit behavior. Okay? So so here's an example. Suppose these are independent random variables which are plus or minus 1 at probability half. And there's a very simple example. So you just take summation xi xj over all distinct I and j and divide by n. Okay? So this it's basically summation xi over root n squared minus something. Okay? And this is a limiting distribution, and it's not a Gaussian distribution. It's a centered chi-squared distribution. However, if you do the small perturbation of one coordinate, you get this kind of thing, 1 over n summation xj j not equal to I. So this is typically quite small because the xi's are independent mean zero random variables. The influences are quite small, but you don't, with the proper normalization, you get a distributional limit which is not Gaussian. Okay. So just the smallness of these perturbations doesn't guarantee Gaussian behavior. So what is it that guarantees Gaussian behavior? So these, theorems based on influences on these small perturbations, how things change if you change one thing, these are, as I said, they're widespread in the study of fluctuations. So people study fluctuations of random objects quite a lot using this these things. But can you extend it to the study of central limit theorems? So it turns out that you can still formulate a heuristic using these influences. This was in 2008, where I showed that if the influences are not only small, but are also approximately independent, okay? So it may be difficult to write a random variable W as a sum of independent components, okay? As I said, in the minimal spanning tree. It's difficult, I don't know how to write it as a sum of independent components or approximately independent things. But if you look at perturbations, when you change one coordinate, how it changes, that's a very well-defined quantity, okay? And then you can ask whether these changes that you get, if you change one quantity, so for instance, in the traveling salesman, you have n random points thrown down on the unit square at random, and then you look at the minimum length path through these points. And then if you change one point, the location of one city to somewhere else, you can ask how much does the traveling salesman optimal path changes. And that's a very well-defined quantity. And what I'm saying is that if these quantities are approximately independent for most pairs, then you can expect central limit behavior. Okay? So that's the main idea. So Stein's method, also studies these small perturbations, but in when I started studying these things, the existing version of Stein's method, you need some kind of structure, various kinds of structure for the method to go through. So I was looking for something a bit more general. So the proof of this, so this is not, this is the theorem, and I'll show you the theorem, what the theorem exactly is. And the proof uses Stein's method, and I will give you this proof and statement shortly. Okay, so any questions? Yes?
So earlier you said that one expects central limit behavior for the MST,
Yeah.
but that the original heuristic doesn't apply.
Yeah.
So why do you expect it?
I don't know actually. I mean, I don't know. So Alexander, proved it in 2 dimensions, and then Keston and Lee in 3 and higher dimensions, and that was 20 years ago. So I don't know what motivated them to prove that. So probably people knew that, that you have central limit behavior, because if you change these kinds, so there are optimization problems where you don't expect central limit behavior, and there are optimization problems where you do expect central limit behavior. And I'm not sure. It's just folklore, and some people say that some things should be Gaussian, and maybe simulations have a part in that, maybe other knowledge, but I don't exactly know. Okay. So does this heuristic work for the minimum spanning tree? This one that I just presented, it does. Okay. So by the way, Keston's proof was using martingales. So he found, Keston and Lida found a martingale, or they worked with a martingale that whose endpoint was the total weight of the minimal spanning tree, and they analyzed that martingale. So if the weight of an edge is perturbed, how much does the weight of the tree change? Okay, you can show that it's approximately equal with high probability to a function of the edges that are close to this edge. Okay.
So you are talking about the lattice or general?
Well, for now the lattice. Let's say you were just talking about the lattice. Yeah. So if you just take the lattice, you change one edge weight, and how the total. Okay, so you take a big chunk of the lattice, and how the total weight of the minimal spanning tree changes, it depends only on a small neighborhood. Now, the thing is, the size of the small neighborhood is intimately connected with the behavior of critical percolation. Okay. So that's why Alexander, okay, they did it in the continuum, so they did with continuum percolation. But anyway, let's imagine the lattice. That's why Alexander could do it in 2 dimensions, where he used the Rousseau-Simon-Welch theory. But Keston found a way around that somehow. Keston and Lee, you can do it in higher dimensions also, but you don't get a rate of convergence. Okay. You don't get a rate of convergence. You just have monotonicity formula. But anyway, coming back to this, once you realize this, which is a non-trivial fact, it's a non-trivial thing, then it's clear. Then you know that if 2 edges are far apart, then these perturbation things, these influences are approximately independent, because how much the weight of the tree changes, you can write it approximately as a function of things that are close to that edge. The thing doesn't go out. Okay, so it stops after a while. And since most pairs of edges are far apart from each other, this perturbative heuristic that I mentioned implies that W is approximately Gaussian. Okay, so there are many things. I'll tell you a little bit of how this was applied to other things, but most recently there was this thing about the minimal spanning tree. We got some, so with my student Chan Cheng Chen, we got some rates of convergence in the central limit theorem for minimal spanning trees. Okay, so for instance, here's an open problem, the traveling salesman. So endpoints are uniformly distributed on the unit square. Ln is the length of the minimum length path that touches every point. And it's widely believed, I don't know again, to answer Russ's question, I don't know why, but Ln should satisfy a central limit theorem. Okay, so according to the perturbative heuristic, one should be able to show this if one can prove that the change that occurs in this length upon changing one thing can be written approximately equal to something which depends on a small number of points in the neighborhood of that point. So if you can show this kind of thing, then you can prove the CLT. So for this, upper and lower bounds on the variance are known and various other things are known, but the central limit theorem seems to be out of reach. So there are many other problems where this heuristic may give a possible unified approach once somebody figures out how to prove this kind of thing, that small change. So for the minimal spanning tree, proving that a small change in one coordinate results in a change that depends only on a neighborhood, this is very specific to the minimal spanning tree. It uses facts from critical percolation and other things. So in general, it's not known how to prove this kind of statement. Okay, so the formal statement of this perturbative heuristic. Let X be a vector of independent random variables. Let W be a function of X. And let X prime be an independent copy of this vector. Okay, so you have a vector, and you have an independent, so X1 prime to Xn prime are all independent, and are independent of X1 to Xn have the same distribution. Okay, and then for any subset of integers 1 to n, you define a vector xa where you have flipped the coordinates that were in A. So you have replaced the xi by xi prime if I is in A, and if you have kept it xi if I is not in A. And then you let del I of f, as usual, you flip one coordinate, look at the difference. Okay. And then you additionally define del I of fa as you flip one coordinate, but not in x, but in the vector xa, where you've already flipped everything in a. Okay, so it's you have already changed everything in a, but then you change one more coordinate. Okay. Any questions about the notation?
X is also consisting of independent variables?
Yeah. So if x is a vector of, so x1 to xn are independent. So yeah, I'm considering functions of independent random variables only. Okay, and then you define some number, nu of a, so you attach a weight to each set, subset of a, and a subset of 1 to n. And let Ti be this weighted average. So nu a, del I f, del I f a. So it's a weighted average of, sort of squares of influences. Squares, so influences are sort of squares in some sense. So it's a sum of these things. It's a weighted average. You can check that this is actually sums to 1. So the weights sum to 1. These are non-negative weights which sum to 1. And this Ti will be our measure of influence of xi on W. So it's not exactly del I of W, it's a somewhat changed version of that, but it's basically that. I mean, you look at how your function changes if you perturb one coordinate, and then you combine it in a certain way. And this is actually closely related to what are called Shapley values. So in coalitional game theory, there are these things called Shapley values which measure the influence of one voter in a coalition. So these are very closely related to that. It's the same set of weights that you have. Okay. So the heuristic is that if TIs are approximately independent or even uncorrelated, then W is approximately Gaussian. So I'll state the theorem in the next slide. So you see, you have an arbitrary function of independent random variables. You construct some influence measures using that, and then you are claiming that if these influence measures are approximately independent, then W is approximately normal. So let T be the sum of the TIs, and what I mean by uncorrelatedness is that T has small fluctuations. So if the TIs are independent, you can expect that T has a small variance. Okay, so relatively small variance. So the fluctuations cancel out. So here's the theorem. Suppose the expectation of W is 0, variance of W is 1. Then the Kolmogorov distance between the distribution of W and the standard normal distribution is bounded by sum of two terms, the standard deviation of T and this part. So the first term measures the independence of influences. Okay, so if the standard deviation of T is small, it means that these influences are approximately uncorrelated. Okay, or maybe negatively correlated, whatever, but at least not positively correlated. And this measures the smallness. So you also need that influences are small. Not only they're independent, but they're also small. So the second term measures the smallness. So this is a completely general result, which takes any arbitrary function, looks at how how things change if you perturb one coordinate, and constructs a random variable out of that. And if that random variable has small fluctuations, you can expect your original thing to be approximately Gaussian.
So this variance of T is what's big in your sum of xi xj case? What is the heuristic there?
So in summation xi xj, the del I if you perturb one coordinate is 1 over n summation xj j not equal to I. So you see these are approximately the same for every I. So del IFs are very dependent. So this T will have a large variance. Okay. So TIs will all be roughly the same in that example. And thanks. Okay, so the proof sketch, since I have a little bit of time, we started late. So first recall the notation. X is a vector of independent random variables. W is a function of x, means 0 variance 1. X prime is an independent copy of x. Xa is a vector where we replace everything in A by independent copies, where A is a subset of 1 to n. You define these discrete derivatives, and define this T to be a weighted average of products of these discrete derivatives. So that's the summary of the notation, in case you have forgotten. And in the last 5 minutes, I will give a sketch of the proof of this result. So first, for any functions g and f and any set A and any I not in A, note that expectation of del ig times del ifa can be first written like this, because del ig is gx minus gxi. Okay. Now, the crucial step is that if xi and xi prime are interchanged, this expectation will remain the same. when you interchange xi and xi prime inside this thing here, it just becomes a negative of this. Okay. So that's something that you can verify, that if you change xi and xi prime, del IFA becomes negative of del IFA, and this thing just becomes gx. So you get 2 times this. So now if g is some function phi composed with f or some smooth function phi, we get by chain rule del ig is approximately phi prime w times del if. So approximately because these are discrete derivatives. And so if you start with phi prime w del if a, you first from this step you get this. And then using this, you have 2 derivatives, you somehow remove 1 derivative, you just land up with 1. Okay? So this phi prime becomes phi, and this product becomes just one thing. Okay? And then this expectation of phi prime w times t can be written using this identity. So t, remember, t was a sum of products of these derivatives. Now it's just a sum of derivatives. You have removed one thing. And this sum is actually very simple. So this sum, it's just an algebraic identity. It's just fx minus fx prime. So you're just going from x to x prime. You're replacing everything. And so what you get is, at the end, is that expectation of phi prime w times t is approximately equal to expectation of phi w times w. So that's the main thing. So you have a random variable w, which is a function of independent random variables, x1 to xn, some arbitrary function. You define t in a certain manner so that as long as these del ifs are small, these influences are small, you get this approximate identity. That expectation of phi prime w times t is approximately equal to expectation of phi w times w. Okay? So it's a completely general thing that you can do for any random variable. Now, if by chance, so one thing, note that if phi is the identity function, you just get expectation of t is the variance of w is 1. So you get a measure of the expectation of t. You get it's equal to 1. So actually you can see like exact equality will hold. And now if it turns out, by good luck, that t has small fluctuations, then this random variable inside the expectation can be replaced by its expected value. Okay. So that's the main thing. So it can be replaced by its expected value, and you can just move it out. Okay. And as soon as you do that, you get Stein's, the approximate Stein equation. Expectation of phi w times w is approximately expectation of phi prime of w. So that's the idea. You have an arbitrary function of independent random variables. You somehow cook up this t, which is a sum of influences, in such a way that you have this approximate identity. Okay? And this approximation depends on how small the influences are. If the influences are small, then this approximation is good. And then, of course, then if t is like a constant, you know that w is like a normal random variable. So this is the main thing. Let me quickly summarize. So Stein's method is a powerful tool for proving central limit theorem in the presence of dependence, many variables. The perturbative heuristic is a method that is an attempt to give a unified approach to understanding central limit behavior for very complicated random variables. And the heuristic says is roughly that if the random variable w is a function of many independent random variables, and the influence, and 2 conditions are satisfied: if the influence of each xi on w is small, and if the influence is approximately independent, then w may be expected to exhibit central limit behavior. So this theorem has been used to prove central limit theorems in statistics, in random matrix theory, in number theory. So I have some joint work with Kannan Soundarajan and some other areas. There is a continuous version of this also. And there are lots of open questions, as I said, only a small fraction that I mentioned here, so which may be approached by this method.
Thank you. Any question, comment?
I have a quick question. So can you adapt Stein's method to make it work not for the Gaussians, but for another stable law, or maybe?
Yeah, so lots of work has been done, and so there is a bigger expert right sitting right behind you, Louis Chen, who knows. So he was the first to do the Poisson approximation using Stein's method, and various other things have been done. And there is a general distributional approximation. And Andrew Barber has done it for function space approximation, so you can do for processes. And there is a recent work on Malevin calculus and Stein's method, which attempts to do it for processes.
See, so for example, in your counter example, we have 1 over n sum of xi, xj's.
Yeah.
So I guess this thing is converted to some
Centered chi-square.
eternal.
Yeah. Yeah, so you can do this. So the dream would be to do Stein's method for Tracy Wheeler.
Thanks.
Any other question, comment?
Just any comments about a multi-dimensional version of your results, so when f is vector valued?
So I haven't worked in multidimensional versions of this specific result, but there are multidimensional versions of other versions of Stein's method. Let's say the method of exchangeable pairs. It has a multidimensional version. But this one I haven't pursued, but it is very conceivable that if there is a good problem, I'll be willing to think about it.
Any other questions? If not, there's one gift from a local organizer. I don't know what that is.